Hello. Check.
Yeah, it's working.
Perfect. Wait, Pranama. Or should we wait for a little bit?
1 minute.
Yeah, no problem. I'm in no rush.
Proper. That is not coming, but there right it's proper. Yeah, it's called.
अरे मालूम पड़ा मैं कुछ बोल रहा हूँ मालूम पड़ा सब कुछ रिकॉर्ड हो रहा है check so now I know where my controller is then so should I go or should I wait for another minute or two? It's good. Okay, so there. Just need to activate this window. That was me? No, I thought that was my voice. Not delay bhi nahi hona chahiye. Okay, so, alrighty, let's go ahead and get started. All right, folks, welcome back. Session 3, day 3. We've been talking so far about different aspects of electric machines, right? I mean, like this is one of the early projects that we did, and we have a couple of publications related to this topic as well. And the reason I wanted to bring this up is because when you're talking about concepts like health monitoring, condition monitoring, fault tolerant operation, there is a substantial value in knowing when a fault is about to happen. So the way we approached the problem was a little different. It was slightly more invasive than we would then. Sometimes it's practical or doable unless you are going for a brand new application. And our idea was to go for something very straightforward. So let's just, I'm going to skip over the PMSM components because this is something we all know. There's not a whole lot of change we're seeing here, right? I mean, like what we have really is you have the overall machine, you have the PM design. What basically I wanted to highlight here was that permanent magnet machine has flux flow in it. Right? You basically have flux that goes from one pole to the other, closes this loop. Now, when you start talking about this, the fundamentals of basically the idea of rotating reference frame, right? You've done this for field oriented control. The idea of moving the observer from the stator to the middle of the air gap to the rotor, that's essentially what Park transformation and Clark's transformation is, right? So what you do basically is you can convert the system from a three-phase system to a two-phase system, which is moving in space, and then you move it from a two-phase moving system to basically you go from ABC to alpha beta, and from alpha beta you go into DQ, and that allows you to go from a moving two-phase reference to a stationary two-phase reference. So that was the basic definition. Now, when you start talking about the idea of PMSM or for a permanent magnet machine, it's that you need to remember that your converter at the end of the day is being controlled. What you have access to are the terminal measurements. So when you're doing the terminal measurements, your entire selection of your switches is a function of the vectors that you have defined. Everybody here has probably come across space vector modulation, space vector PWM at some point. If you haven't, it's a simple enough concept that you can look it up yourself. But if you have any questions, I'm more than happy to answer. But the idea really is that you have an input, you have the reference input, which is your commanded speed. And then you have which basically goes to the PI controller, generates a reference current. And from that, you create the two components of Q and D that is fed to the space vector modulation unit. And that gives you switching signals that you can send over to your inverter. So the topic itself is fairly well established. The part where it starts to look a little bit more along the lines of fault detection is when we start looking at the concept of eccentricity. So when you look at, we have talked so far about structural, we talked about the issues, we've talked about fatigue, we talked about fatigue fractures. We haven't, like I said, we haven't spoken a whole lot about shaft. That was the one topic I did not cover too much of. There are some reference articles, at least there's one that comes to mind. I'd be more than happy to share with you, and you can read through it. But the idea basically is that for motors, if you have any imbalance, you can have situations like static or dynamic eccentricity. So this can happen because you have metal fatigue, you can have unbalanced stress, you can have improper installation, and of course you can have corrosion. We've talked about what causes each one of them in detail over the last 2 or 3 days. So if you look at this, the basic definition of your motor is that you should have a uniform air gap across the entire motor, right? There should not be any variation. And that's an assumption we always make, assuming that the bearings have been mounted properly, that the phase windings has been done properly. One issue, for example, you might have is that you might have wound for certain kinds of machines, or in our case, the concentrated coil, you might have wound it backwards or connected the terminal backwards, which means you will have a flow of flux that is going to go, let's say, downwards as opposed to towards the back iron. So static eccentricity basically is a condition in which the center of your rotor is offset by epsilon. So it moves away and it spins in place. So it's a finite shift, but it's a static shift. Dynamic eccentricity basically is a condition in which it moves and it wobbles. So it basically keeps moving around the entire motor. So it doesn't stay put in one place. So the center itself is moving. So that's the condition. So if you add to that the issue of eccentricity, the other kinds of faults you can see, you can have a case in which you have uniform demagnetization. That's not entirely very typical unless you have temperature effects that have affected the entire permanent magnet setup. You might actually have some of it that are exposed, let's say localized heat spots or otherwise. But you can have uniform and partial. They are at least methods that you need to have an understanding of. So what can cause demagnetization? We talked about this. We have temperature, cooling, malfunction. You can have aging of the magnets, corrosion, or you apply the improper armature current. So this can also happen because you had a short. You applied a certain amount of voltage, and that caused current that was much higher than what you thought it would go through. And that creates a significant issue. Just to give you an idea, this is just the flux density from a set of magnets. And in this study, we basically set the permanent magnet to have 50% demag, just as a number. We did not percent. So the idea is that what this tells you is when you have a demagnetization, it's a field that if you find a way to read that number, if you find a way to read that quantity, you can tell whether or not there is a demagnetization. We saw this BH curve this morning. When you're talking about different permanent magnets, alnico has a high heat tolerance. Samarium cobalt has very high as well, the ceramic, and then there's neodymium ferrite boron. As you increase the temperature on the operating point of base starts to move downwards. Now, common faults, if you're looking at it and you start talking about the winding failure, you can have interturn short in one phase, you can have shorted between phases, you can have phase to ground, or you can have phase to stator itself, the back current, in which, let's say, the slot liner is not there, there is a partial discharge, insulation gets broken down. So it has to be a sequence of events, but you can have a short that happens. So these are some pictures. These are not from our lab. These are actually pictures that we did. It's actually a set of images that we had from Brazil, and in which we have specific faults that they induced to show what the motor would look like. And the reason that can cause insulation failure, once again, we've talked about this, is manufacturing defect. You can have temperature and cooling, overloading, high voltage, that's DVDT, or you can have friction that's caused due to vibration. So how do we go about this? If we are talking about the traditional fault tolerant fault diagnosis schemes, you can have like a couple of broad buckets you can put everything in. The first one is spectrum analysis. Look at what harmonics your armature current puts out. You can look at the vibration spectrum. If you want to do vibration analysis, you have a few ways to do it. You can mount an accelerometer on top of your motor. You can have a piezo sensor that's put on the foot. You can have a piezo sensor mounted around the body. So there are different folks who have done vibration analysis in different ways. You can also have an axial flux spectrum analysis, in which you're once again trying to identify what the field distribution along the z-axis is. In terms of parameter estimation, you can have it based on current and voltage. That's a little more popular because it doesn't require you to do anything, doesn't require you to add any new components. Instead, all you're doing is you're looking at the -0 sequence for the current, voltage, and the impedance. So if you combine that with the idea of temperature monitoring, if you have let's say you have a thermocouple that is placed inside your, thermistor that is placed inside your motor, that can give you temperature reading. So what we are finding even now as we're doing this work is that adding temperature as a variable gives you valuable information, specifically when you're talking about fault detection. The sequence of activities that, or sequence of action that you would follow is you acquire data, you identify the signature, and then you essentially, these are the steps that you typically follow. You have a pattern recognition, extrapolate the trend, and then predict the failure. So the idea is you start off with the known components, gather all the information you have available, and then create basically a definition of what a healthy machine looks like. Any deviation from that is seen as a signature. It's seen as an indicator of a fault that exists somewhere in the motor. So if you're looking at the common faults and fault diagnostic techniques, you can have issues that happen in your bearing. So if you have a bearing fault, this is where it shows up. If you have an issue in the bearing, you can use current frequency analysis. You can also have vibration and noise frequency analysis, but none of the other two methods would work. For eccentricity, of course, you would have it in current and vibration. For winding short, you would see it in current and you would see it in temperature, but you would not necessarily see it in vibration frequency measurement. This is based on classic literature, by the way. In partial DMAG, we actually had current frequency. Once again, it shows up. And the second one is based on the parameter estimation using current and voltage. We actually have an article that we published some time back that talks specifically about the different kinds of failures, this specific idea of what the failures look like and how you can do condition monitoring. This is a review article from a few years back. If you want, I'll be more than happy to share. So, but the challenge is when you're talking about something like this, there's always an associated hardware requirement. For current frequency analysis, you need to make sure you have a current sensor and an encoder. For vibration sensor, you have to have an accelerometer, or you have to have a sound recorder and an encoder. For parameter estimation, you have current sensor, and for temperature monitoring, you have a thermograph, which basically could be any temperature monitoring device. You could have a thermistor built in. But the challenge is that they are not always applicable for everything that you're trying to do. So the requirement of hardware is not something we are shying away from, because what we established, at least as part of the study, was that sensorless was not necessarily the solution we were trying to go for. We were trying to find accuracy, and more importantly, we were trying to at that point look at what does it take for the system to go offline. I mean, rather, what does it take to get this for the system to go offline, and how can I avoid that? So we were constantly trying to eliminate a possibility where the system could have to be taken offline without plan, basically an unplanned outage. The first two methods are not good for different operating speeds. Eccentricity and DMAG have the same frequency signatures. That's why it became a problem. When it came to parameter estimation, you basically need to know what the fault-free machine accurate parameters are, and manufacturers typically will not give it to you. And of course, temperature monitoring, temperature itself is affected by many factors. You can actually have, like I said as well before, you have everything starting from coil winding to an insulation failure can directly cause a change in temperature. So it's not that any of these are not right or adequate. We just found that they did not solve every single failure that a permanent magnet machine could have. So the question then we raised was, okay, fine, if nobody has done what we think they should have done, then what do we want to do? So we defined that we don't want to be influenced by the power electronic device harmonics. That was a big deal for us. We wanted to make sure that if the power electronics is going to spit out any harmonics, we don't want that to overlay on the signature that my motor is seeing. We should be able to identify different faults, and more importantly, we wanted to make sure we identify the severity. Why? Because that way, when a fault is just starting to happen, we can catch the failure before it becomes catastrophic. We don't want to have machine parameters because, once again, manufacturers don't give it to us. We don't want to ask for it, and we want it to be low cost. So low cost is something that, depending on how you define low cost, whether it is part count, we don't have very many parts here, but the method that we came up with is invasive, which means there is a certain amount of cost associated with installing the setup. So this was the motor that we had. We developed, it's a concentrated coils that we had, and we installed what's called a surge coil. Is everybody here familiar with the term surge coil? Anybody here who's not? So don't worry about it. So surge coil really these are coils that are installed inside a motor primarily to monitor the flux field distribution inside the machine. So oftentimes they are given in prototypes. In some cases, you might even have commercially available machines. They allow you access to thermistor. They might have a phase one or a surge coil that is placed for a high performance or a high efficiency application. But oftentimes you only have one, or typically you would have two of them at most that is given for an application. The motor we were using was actually a low power motor that was easily available because we recognized we had to have more than one motor because we were going to damage it, because by definition we were going to break stuff. And the second thing was we wanted to make sure that it was a setup that was reasonably scalable. And if you're talking about a much smaller motor, if we can identify a signature for a small machine, then identifying it for a bigger machine is going to be typically easier. It was 15 amp draw, so the current draw itself was quite reasonable, but it was a 12-volt motor, and that's what made it a little more distinct. So if you do FE analysis, you've seen this before. You can mesh it, you can plot it, and it gives you a 4-pole design. And that essentially gives you the field reconstruction concept once again. Except what we're doing here is not field reconstruction with the phase winding. What instead we are doing is we are trying to use a surge coil to break down that same exact component of field that we talked about at the beginning of the session yesterday. When we talked about microscopic energy conversion, we were talking about the fact that if the field rotates, you can actually create, you can measure the voltage across the phase coil. Well, guess what? If we have another turn, another winding that is sitting in the motor that is unenergized, you can still measure the same voltage. So the question really is, what does this surge coil need to be? It has to be an unenergized coil, still made out of copper, with the same material properties that you had before. So you are invasive in how you are approaching it. You are adding an extra coil into it. But the basic principle still follows Faraday's law. The number of turns you need to have is a function of how much current you're applying, because that will cause the field, and N dphi dt will dictate how much N you need in order to make sure you are visible. I believe in our case, if I remember correctly, we had 3 turns on our motor. So we put in 12 surge coils into it because we wanted to start there. And the idea was, if we were already winding, and a lot of times when the motor is being basically sent back for rewinding, you can add surge coils into it. So our expectation was you don't have to pull the motor offline to put surge coils. But instead, if you're talking about an HEV or EV application, when you are making the windings, add an extra surge coil. Or when it's being rewound, you can just drop in the surge coil, because there is no unique requirement of these surge coils. We put 12 of them specifically with the purpose of being able to measure every one of them. This is the idea of co-simulation. For those of you who have never done that, it's a very powerful tool or a very powerful approach in coming up with the solution of a model where the power electronics is coupled with the machine behavior. And the reason we wanted to do that is because we wanted to see how our converter was going to operate when it comes to the electromagnetic behavior. So we have surge coil voltage that's going in. It has to be processed. So the one thing you will notice is that there is always noise. On any signal, anytime you measure the voltage across the phase windings, you are going to get noise. This is no different. You're going to get some noise, which means you have to have a filter that allows you to actually clean up the signal and send that over to your space vector module. Co-simulation, once again, this was the overall layout. We used, at that point, we were using Infolytica. Our inputs basically were the phase voltage, and the output was position, speed, and your magnetic force. There were 3 currents that go out. Your full co-simulation model is completed. So it takes a little extra time in the simulation. As you noticed, as I was talking to you guys yesterday, we switched over from having an actual FEM model here for co-simulation to replacing this with a behavioral model. That made the system much faster. But the idea was still the same. We wanted to we didn't want to decouple the behavior of the machine from the power electronics, because here we are sensitive to frequencies. We want to know what frequencies, if any, are being pushed out. So this is the actual setup here. We had the DSP controller connected, that's in the back. We had Fuji gate drivers based converter setup here. We had the switch module that was there, the inverter module. Surge coils were connected, and then we added basically a data acquisition card by MathWorks. So it was a MATLAB data acquisition card, DAC card from them. And all we did was we just kind of plug those numbers into our DAC card. The reason for that was because that just made it easier. You can replace that with a microcontroller. You can replace that with any other system that can gather the information. The output, one of the questions I was oftentimes getting was how thick the wires are, or how much it actually, so it's not giving away. So, or how much of the, how thick the conductors are. We only had, like I said, 3 turns. So the wire in comparison, it is much narrower. So arguably, you could put that within the shield that you have, the insulation, if that is how it was to be made. But that would mean you have to have a dedicated, basically, power line that is being sent out. But that's possible, right? People do that kind of stuff. The principle basically is collect the data online, filter it, decouple it, and display it. Decouple what? Basically, you're decoupling the armature and the field components. You're separating them out, splitting them up to see where the fault is. So in terms of filter, we did an FIR low pass filter. We did a stop frequency of 1 kilohertz, and then your pass frequency was 500 hertz. And that basically corresponds to 7,500 RPM for this motor, which was a 4-pole design. So once you filter it, basically you have the voltage that comes out at the surge coil. Keep in mind, you're still getting the same choppy signal. Once you filter it, it starts to look clean and a sinusoid because it has an average that moves in a sinusoidal fashion. In terms of experiment results, this is basically for the surge coil voltage with vector control and surge coil voltage after the filtering. This gives you an indication of a healthy machine, which means everything is symmetrical, everything is normal. Now, in terms of decoupling, we basically decoupled our system. So we were basically using the same method as you would use for going back from your vector control. So we decoupled the system into two basic components. We have the armature component and we have the field components. One thing you will notice is that at different loads, your plot basically is just a spider graph. So basically all of them, they move at different, basically the radius of your graph is different for different percentage loads. There's a very small variation in my field. So you cannot see a load change as clearly on the permanent magnet side. However, what you do notice, and this is from hardware, what you do notice is that the entire, all the surge coils are measuring nearly the same voltage, which means when the machine is healthy, the measured voltage across all of them is the same. So we started breaking things one at a time. So the first thing we did was we induced, we caused static eccentricity. We moved the entire thing off by a certain margin. I think we added, 0.005, 20% of an inch and 0.01 inch of static eccentricity. What we found was at 20 and 40%, you do see a shift in your measured voltage across surge coils after filtering. This is in the field component. Why? Well, because your eccentricity is directly going to be seen on the permanent magnet. In terms of eccentricity, you can also see in the dynamic eccentricity where we move the shaft away. You saw that this is just for a one-time snap. So you will see that it actually also is visible and measurable. If you do interturn short circuit, in that case, the PMSM can have 1, 2, or 3 turns on the armature coil around the tews, which gives you, this is specifically shown for 0 degrees. And you can see at 0 degrees, you see there are multiple turns that have been short. The first is 1, then 2, and then 3, and the blue one is a healthy machine. So you start to see a pattern emerge where every change that you have in the system starts to reflect itself on the measured voltage. Can anybody tell me why? The surge coil has value? Why could we not just do this with the phase winding? What do you think? I mean, it's absolutely okay to be wrong or to have a different idea. What do you think? What would have happened if we had used phase windings instead of surge coils? Think about the fact that your power electronic converter is tied to your phase winding. To the very least, you are going to couple your power electronic response, the harmonic response to the power electronics, with the response that you're going to get from the voltage. So if you're measuring your terminal measurements, you don't know whether you're measuring the harmonics because of the motor or if you're measuring the harmonics because of the power electronics. So you have to have a system that is isolated from at least the power. That's one of the reasons why we went for the surge coil. So this is the phase to ground short. Now, this is easy to spot because the numbers really go far off. Partial demag, and I'll show you actually how we did the demagnetization. It was less demagnetization, more chipping away. So because we could not demagnetize it selectively in percentage. We are not that good. So in terms of the PMSM, we had 20% or 50% demagnetization, and you see that your field component starts to move down as it starts to demagnetize. And it's not only the point where the demag happened, because demag could be a little wider. It's not a point function. It's a little more spread out. Uniform demagnetization, that's not very typical. However, it can happen. We wanted to make sure we did see how the system would work and uniformly changes the measured voltage. That's how we created eccentricity. Basically, when we were doing this, we started to burr out. So where the bearings were sitting, we started to burr it out, and that would cause my bearings to wobble. So we created eccentricity into the motor specifically, and we ground the plates, and that essentially created a little bit of a shift in our motor behavior. So when you're looking at the experimental results here, the previous one was simulation. I said was experimental, previous one was simulation. So when you see this here, this doesn't look like very much because of the frequency when the time scale is very large, right? So it doesn't look like very much, but once you start looking at the interturn short circuit in which you can switch between two modes, the fault free and 4 turns shorted. So what we did was we drew the wires out to create the fault. We first connected it and then we snipped it to basically see how this behavior would be. In the interturn short circuit, this is the measured quantity. It actually is observable on my surge coil. For DMAG, we actually, like I said, we actually scraped off permanent magnet to make it a non-uniform air gap, because that was the only way we could find a way to change this, the behavior of the magnet. Based on that, we identified that one of these phases, you notice, has a lower measured voltage. The sinusoidal voltage that's measured is lower. That indicates that you have a fault here. In terms of a DMAG, once again, there is a periodic dip in each curve that basically shows that you have, there's a periodic dip in each curve that shows that your rotor has partially demagnetized. So when we did all of this, what we realized is that first and foremost, the benefit was it is not influenced by power electronic devices. It can determine static eccentricity. It can look at short circuit location, severity, and you can identify everything, every fault that you wanted to do. In addition, one thing we found out was that it actually has value as a backup position sensor. I'll talk about that in just a little bit. So the challenge, of course, was that it's an invasive technique, which means you had to crack open your motor to install it. And that actually is a deterrent. A lot of companies don't want to crack open the motor because they don't manufacture it themselves. They have an external supplier who manufactures it, and opening the housing could actually create problems. So that is indeed a consideration that you have to take into account. So based on that, we identified that all the severity and the location, we don't need machine parameters, and the severity of the issues could be identified. But what we realized was that when I apply my current, or when my motor is running and it's healthy, I am getting my phase feedback, my phase current feedback, right? Now, in any control algorithm, I either need, I need information for position and I need information for current. So if you want to do an AC machine control, oftentimes what we do is we have IA, B, C, of which we only measure 2 of them, and we assume symmetry and we say IA plus B is equal to minus IC, right? We just say that that's how it's going to be, and we move on. What we went here was that we have a surge coil here, which is meant for fault diagnosis, which when there is no failure, it is not doing anything. It was a passive component that is not doing anything. So instead of the traditional position sensorless methods would require options like high voltage frequency injection, a back EMF based method, or you can have a flux vector with the machine model. So you can require different things for sensorless control. Instead, what we did basically was we realized if you are already identifying what your the measured voltage, what the field distribution inside the machine is, your magnetic field distribution, if you go back to field reconstruction, magnetic field is defined as a function of current and position, right? What that means is that if your surge coil can actually recreate your flux distribution, in that case, if one of your sensors goes out, then your surge coil can serve as a +1 redundancy system, which means now for an application like aerospace system, where you want to have a lot of built-in redundancies, this could be a potential solution. So we actually defined an operating principle specifically for this, and we started doing a sweep to see what this operation could look like for a position estimator. We created a universal sensor framework that goes around the control option, around the control model. And based on that, we looked at a couple of options. First is we tried to see if we could estimate the current estimation position, the current value based on the DC link current and the switching state, which is what is being done. Sinusoidal current reconstruction with uniform samples, or you have current vector with the machine model. So if you're talking about the current estimation, we created an algorithm specifically that tells us how you would establish each one of your fluxes. And based on that, you can create a function, basically that is, you can write down the differential equation as a function of flux and current. So based on that, we designed a sliding mode observer that could identify whether or not you are getting basically what your current is and what your flux function is. And that allows you to create this overall system, which is a current estimation module. So when we established this and did a test for, this is by the way from hardware, this is hardware. When we identified and we try to recreate the estimated position, we found out that it has a very good overlap between the actual position, which we got from the encoder, to the calculated position that we got from our method. And then we looked at the starting point. The only place where we actually found some issues were during startup. During startup, there's actually a delay of about 1.5 cycles when there is noise that is induced because of the system turning on. So it takes a little bit of time to go into steady state. But in most cases, that is not a problem, because assuming your machine is not damaged from the get-go, you probably won't have this problem. So the next part basically was looking at specifically the estimated and actual DQ currents. You have the estimated value in green, and you have the actual values in red. So when we looked at this, basically what we identified is that the idea of fault detection and health monitoring is actually possible, and search call can be used as a backup sensor. It is quite different from sensorless method. It's not the same idea, primarily because the issue of resistance variation that you typically get from your coil winding, because it's carrying current, can be avoided. It also does not have any reliable any influence from the harmonics that you get from the power converter, and that basically means you get a +1 redundancy. So that was really it. So I wanted to kind of open this up at this point, and I got done a lot faster than I thought I would for the first time at all in this entire season, in this session. So I wanted to see if you had any questions specifically around the topic of fault detection. This has been a topic that I've been working on for some time. Power electronics or PM machines was one, but we have also looked at options like this for using NVH for estimating noise, or for estimating issues in basically, or faults in PM machines and such. So I wanted to see if you had any questions around this topic. So no, not this many. So they only have, like I said, they have max of oftentimes if you're doing a prototype, they would have a couple of search calls that they will provide to you. It's meant to be a probe. It's meant to be a field probe that gives you information about how the flux is flowing to the system. So typically they wouldn't, and that was fundamentally the challenge that they identified, is that we would have to crack open the motor, and therefore we don't want to do this. But there were companies who wanted to take this over as well, and for a whole lot of other reasons that we had to actually put a pause on that. But the idea that they wanted to follow through was when they were doing a rewinding or when they were designing a brand new motor. That was the value proposition that we had created. But no, it is a real concern. So it actually was a lesson to us as well. Is to us, this idea made perfect sense, because in terms of functionality, it did exactly what we wanted it to do. In fact, it gave us more than what we were looking for. We were only looking for fault prognostics. It could actually tell you whenever there is an indication of a fault happening. And then on top of that, it also allowed you to replace any one of the sensors. However, the breaking point that kind of proved to be a challenge that was bigger than others, for an R&D project, it was great. But for industry, for commercial application, you would have to go to something like offshore wind when you talk about much larger machines, or you're talking about, let's say, an option like semi-trucks, something, or aerospace applications, where there's, for one thing, higher currents, where you need redundancy. You don't want something to fall and create a major catastrophic failure. All right. So I'm going to go ahead and stop here. But are there any other questions? Yeah. So in our case, we had a Hall sensor. So the idea was that your motor was working as a censored motor during startup, and we created a real-time failure into the system. So we actually induced a fault as it was happening. We turned off one of the sensors and said, now can this search call pick it up? So at the very beginning, so if you look at the idea for sensorless methods, in fact, so some of the work that when I was a student, there was this work on delta hysteresis modulation, where they looked specifically at the idea of removing one sensor at a time. And they took it all the way down to only one sensor. Instead of 3 is obviously is an overkill, you have redundancy. 2 is enough. It is the number that normally we go for, but they also took it down to one single sensor. And they were trying to do what's called delta hysteresis modulation. Basically, based on your current switching state and the known value of current from the healthy machine, they would extrapolate the information of what the current should look like or is going to look like for this condition. So they would basically create a limp back home strategy for the motor. That was done by a gentleman named Hainan Wang and Professor Fahimi back in the day. So there are methods that have looked specifically at failures that are somewhat catastrophic in nature. But in our case, we started off with the understanding that my position sensor is available and functioning at the beginning. To change the number of poles, you mean?
Yeah. So how feasible it is as an application?
Can you repeat that question? What you're saying is
so for all diagnosis, every people what they do, they'll add something or they'll inject something.
Right. Yeah.
So as for an end product, how feasible it is? Like the companies are
for with basically like voltage injection of that, something like that, a current injection, those are used, those are actually fairly acceptable practices. I mean, depending on what you're creating. So in some scenarios, for example, if you're applying current to an unenergized phase for one of the motors, you might end up creating negative torque. So the question really is, how much torque are you generating? So you have to define, for sensorless methods, you have to define a threshold above which, so we have done some work on switch reluctance machines we'll talk about tomorrow, specifically where we identified what it does if you apply a certain amount of current. So you have to have a sensitivity analysis in the motor to tell you how much current you can apply before you actually end up creating negative torque. And sometimes negative torque is a consequence that you might be okay with, but a lot of times you're not. So yeah, sensitivity analysis is very critical for that. Any other question? Yeah. Depends on the number of phases, right? So it's, if you have very few phases, that's basically one of the selling points for going higher on the number of phases. If you go to 5, 7, 9 phases, especially for mission sensitive applications, then you can actually have enough power or enough torque to basically take you over to the next. You will still see a ripple. There's going to be a wobble that you will feel in the motor. That cannot be avoided because you are basically limping back home. Yes, so that method, that's also been done for a 3-phase machine. In most cases, there are papers that have shown it's possible if you have a phase winding to kind of continue operation reasonably okay, but more often than not, you would see that kind of question being solved by going to a higher number of phases. That way, even if one goes out, you still have 4 phases left. But keep in mind, when you do something like that, your concepts of field-oriented control are going to go out the window because everything, all of your clock transformation, park transformation are built on some basic assumptions, right? So if you do your full derivation for the transformations, you will see that it relies on symmetry. So if you don't have symmetry, now your controller has to accommodate for that. That's what one of our selling points was as well for this idea is you need to know where the fault is so that it can compensate. Otherwise, if you, let's say you have an interturn short and your inductance on one of the phases is lower than it should have been because you have fewer number of turns, n squared over reluctance, n went down, so your inductance basically went down correspondingly as well. What that will do is all of a sudden now Ri plus LdI dt, you end up getting a pretty large burst of, it's a small inductance, so you basically end up getting a change that is much faster than you would normally have expected. So it can actually cause problems because your controller did not recognize there was a fault, and it will start to crank up your current to find if it samples at that instant, it will try to compensate by increasing the current, and that could once again cause the second layer of a catastrophic failure or second level of failure. Oh, without a doubt. So well, yes, it will reduce your motor life, but whether or not it's reversible is subject to how much damage was done. So you will have to replace the winding. So if you have a winding failure in the machine, you have to take it offline. You have to redo the windings. That's not negotiable. But in terms of whether that causes a catastrophic failure beyond that, it shouldn't be as bad because once you take out the copper, there's not much left in it, right? Now, if you hurt the magnet, you created a massive hotspot, and now you have to replace the winding and you have to work through the magnet. So that can happen, but normally you should be able to identify fault one way or the other before it gets to a place where you start damaging other components other than the winding itself. Is that reasonable? Okay. Any other questions?
So for this kind of fault detection, technical switch wise,
it is, yes. So the idea basically, we were going geometry agnostic. So we were going with the assumption that we don't have any information about the motor at all. So which means we are going with the black box. So the idea was when you have a brand new motor, no matter what it is, if it has the flux, we establish what a healthy pattern looks like. And from there, we evolve it to the place of having a failure. So winding functions does require you to have at least some prior knowledge of the distribution that you have in the system. So yes, it is similar. You could actually use that using the available windings in the stator itself. But at the same time, you still have to take into account what you're measuring and the resolution of what you're getting. So yes, simple answer to your question would be, it is possible to look at alternative methods, but this was at that point, it was addressing a very specific need that we were trying to solve for the application. But your point is well taken. Any other questions? It could be anything between the first day all the way to today. If there's any questions, I'm more than happy. We have about 10 minutes before we have to call it officially done. But if there aren't any questions, we can stop. I don't want to keep any longer than you absolutely need to be here. But are there any questions that might be related to other things that you want to talk about, that you want to ask about, basically? Okay, so if that's it, in that case, I appreciate your time, guys. Thank you very much. I will see you tomorrow. Tomorrow we're going to talk about switch reluctance machines. For me, switch reluctance machines is something that I enjoy talking about because I've worked in the motor for about 20 years now. So it's pretty much from the very beginning of my research times that I've been working on SRMs. So feel free to ask any questions. I'm not guaranteeing I will have all the answers, but I'd be more than happy to take a shot at it. Most of the problems with SRMs at some point or the other we have come across. But other than that, please, as what Professor Raghavan mentioned, please try to see if you can think of the question that you want to discuss on Saturday between what you have all the way from today. Friday. Don't send it to me on Saturday. I will not be here. But no, Friday. Yes, on Friday we will have a time. I believe it will be at 2 p.m. That's the third session we will have for the fourth session, right? At 2 p.m. Yeah, 2 p.m. Bottom line is at 2 p.m. Whichever number session that is at that point, we will do that. So please try to send the questions in. It will be really a great opportunity for me also to learn a little bit about your research. And if there are any questions specifically that you have found to be a pain point, if it is something that I have experienced or I have seen work being done, I might be able to point you to some references, or I might be able to give you some ideas on where you might be able to find some solutions. So one way or the other, I would love to hear what you're working on and where you are finding the biggest challenges in your research. So I'm not the Apple Genius Bar here, but I'll do my best to point you in the right direction. With that, thank you very much, everybody. I'll see you tomorrow morning.
Good afternoon. Welcome back to my second lecture. So today's topic is what kind of FEA solvers are there in the commercial softwares or open source softwares, and in what context you use them to solve electromagnetic problems. Okay. I'll turn on and turn off. Thanks. So we are going to look at three solvers: magnetostatic solvers and solvers, or sometimes they're also called as time stepping transient solvers and harmonic solvers. Harmonic solvers, in some softwares, they're also called as frequency domain solvers. So what is an FEA problem? Essentially, we have a problem domain where we have conducting regions, we have magnetic material which has inherent magnetization. You don't need additional excitation there for that material volume to support magnetization, and there is ferromagnetic material that is a good conductor of magnetic field. So our interest is to solve for magnetic and electric field distribution, and say the associated forces, current densities, etc. So what we essentially need to provide is these kind of material excitations and boundary conditions, and what are the circuit level connections. So once we define this, it becomes a closed problem and we can solve for the solution. So we use discretized models, that is, we break it into small triangles and we assign nodes to each of all the set of triangles, or there are also some advanced methods where they use quadrangles and tetrahedrons to solve the FEA problems in 3D in 3D solvers. But today I'll only use 2D theory to explain what different solvers are to be used. Right? There are multiple methods in obtaining this solution. Like, we are essentially interested in getting what is the value at each of this node. There are you can classify them into two major methods, like variational approach based method, and the other one is weighted residual based method. I'll use a variational based method to explain some of the concepts related to the solvers. So here goes the problem definition. We need to solve for this, let's say this A1, A2, A3. I'll only give you a some kind of reasoning type of explanation on how this process is happening, right? And we'll see some simple example to understand what is the background step. Let's say assume that each node of this mesh is assigned a value a subscript I. So there are no 100, and it's just a representative figure. So let's say there are some set of nodes, and we have called them a subscript I, etc. So once we, if we are able to get all these values, that's what the solution we are looking for, right? That set of values defines what is the pattern of field lines, or what is the current density, etc. Anything can be evaluated from there. And one more thing is, we will define a function, let's say capital W a comma a dash. A dash is the differential of a. We are assuming that the energy in this volume is function of a and a dash, right? A and a dash are like this a has also the subscripts, and this a dash is also has the subscripts. As we go into further slides, we'll see how these things get expanded. So yeah, so let's say like how you do in iterative methods. Initially, you have a set of AI values, right? And when the set of AI values in your next iteration are evaluated, your energy value, the energy value gets changed, right? That's the meaning of this WA comma AI. For a set of values, you have some energy. So, if whenever we are calculating something like energy in a volume, we need continuous functions. For example, if half 1/2 mu naught into b square is the energy density in magnetic field, then we integrate it in with dV. So it has to be a continuous function. So these potentials we are solving at discrete nodes. Then how do we have a continuous function, right? So what we do is we represent a local function based on sub functions, like you can see here, n1, n2, and n3. These are called as shape functions. How do we use them is, let's say we are interested in ax comma y, right? In this 2D domain, we are interested in ax comma y. Then that we write it as a function of a1, a2, and a3. And their weightages of a1 is given by n1 x comma y. So for example, let's take n1 x comma y. How this is defined is, when you are at a2, n1 value is 0. And again, when you are at a3, n1 value is 0. Where it is 1?
N1 is 1.
N1 is equal to 1 at what node? Yes. Similarly, the same logic applies for all other nodes. You use simple trigonometric identities to get what are these shape functions to represent this unknown ax comma y in a1, a2, and a3. Right? A1, A2, A3 are simple scalars, like like say 10, 10.5, and 11. What we are saying is the value in between within this triangle is governed by what are the values on the nodes, right? So we solve for values at the nodes, and for evaluating something like energy, we use this kind of shape function based interpolation. Right? And these n1, n2, and n3 have to be used only within that triangle. When you go to the next triangle, the n1, n2, and n3 change, right? So, okay. So this energy function at a comma a, okay, a dash is I think I said it, but let me say it again. It is it's the differential of a, right? Let's say at each node or at each point in the problem domain, the small w based function small w of a and a dash defines what is the energy density at that point. Right? Then we integrate over the volume to get the system level energy. we'll look at one example function of how does small w look like. So when you have the final solution, then if there is a small variation in A and A dash, then that change in energy should come out to be 0. Let me explain this in some numbers. You have you are, let's say, iteratively solving what is the value of A1, A2, A3, etc. in this space. You have arrived at 10.1 for A1 and some 11.1 for A2, A3, etc. If that 10.1 becomes 10.11 and the next node becomes 11.11, then the energy difference between that iteration, the earlier iteration, and the current iteration is nearly 0. At that point, we say that we don't need to solve for further. So this is called the variational approach. We solve for the set of A1, A2, A3, etc., such that any more small variation is negligible. It's something like finding a minimum of a function. Once you reach that belly point, you don't need to, I mean, you are almost as close as numerically achievable to that minimum point. So there is some involved variational calculus based method to show what actually this implies on this function. So if this A is a function of x comma y and A dash is also a function of x comma y, then this energy density function, in this electromagnetics, I'm using energy density, energy as a parameter to check whether we have reached the final solution or not. But in another domain, it can be some other value. In electromagnetics, energy is considered as the measure. So let me call this W as energy density. So this variational of W, when it approaches 0, then this energy density function satisfies this. So this is called as Euler-Lagrange equation. What this essentially says is variation of the energy function with respect to change in A is same as variation of the energy function with respect to A dash, again differentiated with respect to X. It's not just X. If you are, I wrote it in a single dimension. If there is Y and Z, it has another more involved representation. But to understand, I kept it simple. This is something like, let's say if you take y is equal to x square, it doesn't have an inflection point that is not minimum, right? Like y is equal to x square has only one minimum. But if you go for x cube and higher order, it can have a point where the derivative is 0, but it is not the minimum. So to ensure that it is the minimum, we do another differential and say that the second order differential is also approaching 0. So that kind of second measure we use to see that our function has reached the stationary point, where a little difference doesn't change the y, right? In that way, we can understand this equation when the energy density function is not changing much as per this, when energy density satisfies this function, then we say that the set of A values are what we are looking for. So yeah, let's look at an example of what we are saying. So in electrostatics, we know that electric field is defined, is given by minus dV by dx. We have defined a scalar value that can be used to find out what is the electric field. We defined an auxiliary function like voltage for the electric field to estimate, to put it in some kind of known mathematical forms like Laplace equation or Poisson equation, etc. So in a volume, the energy is given by half epsilon naught E square dV, right? So what is the energy density function here? That is half epsilon E square. Is that correct? Yeah. So this E, I'm replacing it with dV by dx. So as per the earlier notation, I'll make this dV by dx as V dash. So this is the energy density function. Further, if I put it into Lagrange's equation, that dW energy density, when you look at its variation with respect to V, and then subtract it from the second expression, it should be 0, because this function, energy density function, is not a function of V. In this case, the first term is 0. That term is not present, right? Whereas the second term, first we have to evaluate how is the energy density function varying with respect to V dash. Then, so it's simply like half epsilon naught x square divided by dx. So it turns out to be V dash, right? Substitute it in the for the d by dx. So it is dv dash by dx, which is d square v by dx square, right? So this is the Laplace equation in a region where there is no charge, right? So what essentially this example illustrates is, if V is the solution you are looking for, then it satisfies the Euler-Lagrange equation, right? We have started it from saying that our the potential that we are looking for also satisfies minimum energy equation, that d of capital W, the total energy value, we equated it to 0 and then derived the Euler-Lagrange equation. Yeah. So this is some simplistic essence of what is FEA. You have some nodes and you need to find what are the A values there. So all we have done in here, we have done in some kind of algebraic sense, but this can also be extended to matrix-based method, which is how it is implemented in FEA solvers, right? So we are solving for the unknowns at the nodes for minimum energy change with change in the values at the node. The set of A values also satisfy the Euler-Lagrange equation. Yeah, one important point is, yesterday I was asking that field pattern, how do we justify that it should go through the low reluctance path, right? Is it there in the Maxwell equations, or is it an additional equation that we are using to justify that? So, so the answer for that is, we have Maxwell equations, and then we know from another theory that if your variable solves Euler-Lagrange equation, then your variable is at some kind of stationary point, right? So based on that, what we are saying is, the electric fields, when you put into Euler-Lagrange equation, they are showing that they are at a stationary point in terms of how much energy they have. Obviously, it will not have a high energy point. It should be a energy minimum point, right? Because you can see the otherwise, like if the fields are going through reluctance, we know that the energy value is minimum compared to any other case, right? By simple expression that half V square by 2 mu naught, we can apply that and see the solution corresponds to minimum energy. And Euler-Lagrange equation also says it says it's a stationary point. So that way we can justify. So what I'm saying is, there is another equation that we use to say that fields take the minimum energy pattern. Yeah. So having said that, let's go into what are the different kind of solvers we are going to see. The way we have seen for electrostatics, that d square V by dx square is equal to 0. There are, starting from Maxwell equations, we can derive some common format equations which go into magnetic solvers. For example, the magnetostatic solvers for this equation solves for this equation that del square A is equal to minus mu naught J into del cross M, where M is for the magnet material that is present in the domain. If you are representing the magnet as a current density, like might have read somewhere that a magnet can be replaced by a coil, right? So in that way, if you don't want to use del cross M, you can replace your magnet volume with some set of conductors placed at its edges, and then have this equation, and then still solve the use the magnetostatic solver. In the transient solver, we solve this equation. Here there is no variation with time. Here there is a variation with time. Again, this can be clubbed into this. If there is no magnet, this capital M will be 0. Similarly, here if there is no any material volume that has inherent magnetization, what is the difference between that J and this J is the first J is called as current due to freely moving electrons. The second J is due to the currents due to bounded electrons. Where do we see bounded electrons that create magnetic field? Like they are there in the material volume, but they are not traveling or taking any path, but creating magnetic field. I said the answer, but still, again, I'm asking. Where are bounded electrons? They're not free to move, but they're just there circulating. Yes, inside the atoms, right? So there are some atoms which have free electrons, I mean unpaired electrons. They're there, they're not coming out, and they're creating magnetic field. If in your problem domain, if there is that kind of magnetic field, you keep it as a separate J subscript M. Whether it is a free current or if it is bonded electron, that first equation that del cross H is equal to J is applicable. Only thing is for implementation purpose, to differentiate between the material volumes that has inherent magnetization, we write it as minus mu J into minus del cross M. Right? Yeah, in the transient solver, we also solve for what is the change in field with respect to time or movement in the rotor. So that is the transient solver. I know that these equations are looking a little bit abstract, but we'll look at some examples in machines case where this makes sense. And the final one is the harmonic solver. Here we are not solving for, we're not solving in time domain, we are solving in frequency domain. Given these are the excitations and they are varying at these frequencies, what is the change? What is the change in phase of magnetic field at a point and at a point 1 and point 2? Like when you solve in phasor circuit, you say that at this point the current has a phase angle of 0. At another in another element somewhere in the circuit, it has a different phase angle, right? When you are solving it in a frequency, looking in AC circuits, and you are solving in frequency domain. Similarly, in the harmonic solver, we are not solving for magnetic fields in time domain. We are looking at, for example, okay, I'll explain more when we go into more, right? So essentially, getting this A value is the FEA step or the FEA solution. Anything beyond that, for example, estimating what is the current density or what is the force, what is induced voltage, what are the core losses, etc., is a post-processing step. Yeah, so let's look into some examples where we use magnetostatic solver. The objective in this kind of activity is to just get the field pattern. We're not interested in how, like, we'll not deal with what is the change in field with respect to time. Examples of where you would use this is you want to understand to what extent the core got saturated or what is the field pattern in the air gap. Those, let's say in the transformers, to what extent the core is getting utilized. Can we reduce the width or height of the transformer legs? Then we use this kind of static solver. Why we actually differentiate between these different solvers is we can, if we write a single solver that addresses all the FE electromagnetic problems, it takes enormous time to solve it. So there are subdivided set of there are different solvers. We can use them depending on what is the problem definition. Again, we can also estimate forces due to the magnetic fields in a static solver. But as I said, the force is again post FES step. So this is an example of how does flux density look like inside inside the air gap. The normal and tangential components of, you can get this kind of information just from a magnetostatic solver. In transient solver, the objective is to solve the field distributions along with the motion and change in the excitation. Right here, we also want to see what is the change in the force as the rotor moves, and at the same time we will also look at what is the change in the current because of the rotor motion. Right? Change in air gap field distribution, etc. If these things are also objective, then also we can use this. Eddy effects are considered as per the theory, like because there is dou A by dou T, this expression involves solving what is the eddy effect inside the machine, but this is not done always. I have an example to explain this. We'll go there. Also, the effects on the induced voltages due to movements are also solved in the model. Right? So more details on this transient solver. This is also called as time stepping transient solver. What we do is what I have explained earlier using the variational space. That or set of that has minimum energy. But when we integrate the circuit relations into the problem domain, to that matrix which has A1, A2, etc., we also add 2 or more rows as per the circuit connections, which what are the current related values, right? So imagine it like there is one physics problem where you are solving spatial distributions, and there is another network related problem where you are trying to solve for the current and voltage, etc. Them in a same matrix, and whenever there are more elements than required, you put there 0. Right. So this is how the both circuit level solution and the FES are integrated. The problem that like you know the field solution at a given time instant. There is an induced voltage in the coil. You also need the information of the next step also requires the information of what is the voltage at that instant and the d phi by dt. But only when you go to that, right? So this is essentially a problem of numerical integration. So once you make that matrix, you can use either trapezoidal algorithm or any of the existing numerical integration methods to address this issue, where when you're going from step 1 to step, you don't have the derivative of step 2. Do you want to use simply the derivative of step 1 to go to step 2, or you want to use some combination like Rangya Kutta or any additional methods? So in a similar way, the circuit is integrated into the solution, and you use a numerical integration method to solve everything simultaneously. Any question? Yeah. So because all this process is involved, and if you also involve keep this dou A by dou T in your FES solver, what happens is, you know that this eddy currents are circulating in small circles throughout the machine, right? So this demands you to increase the mesh elements. So the problem definition becomes bigger, like the matrix size gets bigger. So to address this, different solvers give you options to reduce the problem complexity. One is to cut the machine into symmetric sections and only solve in that small section, right? The second is make the mesh coarse wherever the magnetic field is uniform, right? And sometimes switching off the eddy effects, that helps the mesh creating engine to put a mesh that is coarse in the area where you are not solving for eddy currents. And reducing the time steps, if you know what is your fundamental frequency and what is the maximum expected EMF harmonic in your simulation, then you reduce the time steps, make them coarse as much as possible. One thumb rule that can be used is like you can keep 40 time steps in one cycle, right? So where if that doesn't address the problem in your case, then the next thumb rule you can use is keep on reducing the time step, keep on making it finer. Like reduce it in terms of like keep on making it half. And when there is no change in the solution by less than 5%, there you can stop. So every time you face this question, you have to set up a benchmark simulation. Like I will use this much small time step. So basically, in some cases where I was simulating for 1000 hertz frequency, I found that the estimated resistance is dependent on the time step. So there are so many errors inside, and the circuit and numerical integration, everything is happening. So it's a black box. We don't know what is the estimated value. Only thing that we are relying on is the convergence. So as you keep on reducing the time step, you have to make this benchmark simulation where what is the minimum time step you can use. But if you are looking for simply the field patterns, all these problems are not significant. But if you are using these field solutions and then estimating the terminal quantities, then everything becomes a problem, especially when the resistance and inductances, their PU values are sensitive with respect to the errors you would find in the FEA solution.
So the reduction in time step, it is a trial and error method. You are not getting the result. You further reduce it.
Yes.
There is no written rule or
No. The rule is like you set a tolerance and keep on reducing till you reach that tolerance.
trial and error.
Yes.
Multiple iterations will be required.
Yes. I mean, the trial and error can be made systematic by writing a code that interacts with solver. Just run that code and make that code stop whenever you reach the estimated resistance value in that tolerance. Right? Yeah, I said in harmonic solvers, I was telling what we essentially solve is what is the phase difference between the B field at different points. Why is it important for us is because we are essentially interested in what is the current density in problems like this. So let me go through the key points of the solver. We use this when we are interested in the field penetration at a given frequency. For example, in a solid frequency, solid rotor induction motor, say that at higher frequencies, the field doesn't penetrate much into the rotor core, right? Based on that, you can reduce how much is your solid thickness. So there you can simply run a frequency solver and see to what extent the magnetic field is present. So in that kind of examples, you can use harmonic solver. Because the rotor is solid, there is not much you will see in a transient solver. And similarly for eddy, skin and proximity effects, and also to understand the need for transposition of conductors. We know that let's say in this case, this set of conductors have certain inductance, whereas this set of conductors have different inductance, right? If the stack length is significant, then this inductance can lead to circulating currents. So in that case, we want to see, does this inductance difference really cause enough circulating current that we need transposition in this kind of machines, right? So essentially what I'm getting is like we solve for what is the difference. What we get here is this plot says if you give a current of, let's say, current density of 10 ampere per mm square, here it is 10, here it is about 5 or 6. But what actually the solver gives is this is at j cos 0, this is at j cos 30. But we understand it as there is a eddy effects, and because of that there is a current distribution that is solved in terms of the phase of the current density. In fact, the phase of the magnetic vector potential. So let's see how the inductance is calculated in an FEA solver. So we know that phi is integral of B dot ds for a coil. I can replace P as the curl of A integrated over that surface. Invoking Stokes' theorem, we can write that curl of A dot ds as A dot dl. So which says that if you are interested in what is the flux linkage with this coil, you do integral A dot dl along this coil, right? In a 2D problem, if you just see it through this is a point and this is a point. So what you essentially need to evaluate is A1 minus A2 into L, because in this direction and in this direction A is equal to 0. But in your FEA model there are no points, there are surfaces. How do you address that? Any guess? So this I have explained for a point. To find out what is A1, like assume that this point is conductor 1, this point is conductor 2, and from FEA solver you got what is A1 and A2. Take out the difference between A1 and A2, multiply with the stack length. That is your flux linkage. That's how the FEA solver, let's say, that's how the approach, theoretically set approach to obtain the flux linkage from the FEA solver. But you all might have seen some FEA models. It has the conductor cross section. It is not a point. So it's a square or rectangle. How do you use this concept to get the flux linkage of your phase winding? Any guess? Okay, so we take average. Let's say I have this kind of coil. There is a coil of phase A. This red represents a coil. This is my coil side A1, and this is coil side A2. Then let's say inside this I have a function A1x comma y and A2x comma y. That's not a single value, it's a function. A1 is inside coil side 1, A2 is inside coil side 2. Then you keep integrating A1 over the surface. And this, I think I forgot, we have to divide it with the surface, right? So you integrate it this way and then multiply with the stack length. So this is the background implementation step that every FEA solver uses to give you the flux linkage of a coil that is present in a distributed domain. Okay. So by default, every FEA solver has this kind of post-processing code that evaluates the inductance. Like it gives a test current I, or it gives the current that, okay, it gives a test current and gives you the inductance. So let me take an example of an induction motor, right? I have created an induction motor and I've also modeled the squirrel cage bars. By modeling, I'm saying the bars are shorted. Like as I said in the earlier slide, that we also add the rows corresponding to electrical connections. That means the connections related to the end ring are given to the model. Now on this kind of model, if the default inductance estimation algorithm is run, will it give the actual inductance of the winding? Another question. Okay. I have an induction motor model. Let's say there are some bars here, and the user is supposed to say what is the end connection resistance and inductance if he knows the values. So those values also I have given, and I said that all these bars are shorted. And then I solved this model, and the solver gave me some inductance values. Is that the phase inductance? Reason? Yes. Okay, think it what happens if you have done the same thing in a lab. I gave you an induction motor and some LCR meter. So the measured terminal inductance, is it the total inductance of the winding? I'm asking about phase A winding, not the that circuit inductance of the rotor bars, not the bar inductance or not the rotor side inductance. I'm just simply asking the stator winding inductance. I have given you, let's come to this lab-based example. I gave you an induction motor and asked you to measure the inductance with the LCR meter. Is that the winding inductance? Any answer? Okay, let's take some similar example. Let's say I have a transformer. We always say that induction is equivalent to transformer. So if I short the second and then measure the inductance on the primary, is it the phase inductance? Is it the primary inductance? No, right? Does everybody agree with that? That if I short the second and measure the inductance, it's not the phase inductance. Similarly, in the induction motor, if you take the motor and as it is and just measure the inductance, it's not the phase winding inductance. Similarly, in an FEA solver, you don't have access to what the solver is doing. That's a commercial package or whatever the package. You are not generally going to the background code and telling it what to do and what not to do, right? So the inductance that it by default, in general, what I have seen is this kind of issues happen, or like people think that what are the inductance that is the default results function is giving is the inductance. But if you are interested in taking the values and making a circuit to do further analysis, then you should make a separate model, remove the end winding connection there, and then estimate the inductance. Is that clear? Okay. There are some softwares that do not give this kind of facility, that you have to make the end ring as a separate circuit. You have to tell the solver. I think has anyone used magnet? Okay. In magnet, you have to draw a circuit for every bar. Like this bar is connected to this bar is connected to this bar. In that case, probably it may not give. But if you are sending it to the FEA solver saying there is an end connection saying all are shorted, in that case, what inductance you are getting is some kind of secondary shorted inductance. Okay. How about another example related to core loss and eddy effects? So this is, let me explain this using a PMSM circuit. Let's say I have a permanent magnet machine and I have it on a test bench, and I'm increasing I'm measuring its back EMF and keep on going to very high speeds, right? You expect that the back EMF, the rate of change of back EMF will be constant. I'm assuming that everybody knows that back EMF is given by some back EMF constant into omega subscript E, right? So if I keep on increasing the rotational speed, is the back EMF, is the KB constant? Is there any reason why you should expect it not to be constant? Any hint in the heading? Yes, which losses? Eddy effects in the core, right? So the eddy effects increase with respect to frequency, the losses. So that somehow has to get reflected in the terminals. So is that aspect in the circuit? In the circuit, does the measured terminal induced voltage, its rate of change, does it get affected with omega E in this circuit? How do you say that? Yeah. So there is some loss here, right? In the circuit, we understand that some current is going here, that V square by R. This EB is increasing, so there is more losses here. So that whatever you measure on the terminal, you can write the equation and check that. You can write some Thevenin equivalent voltage to the terminals and see that it is dependent, it decreases. If you take the KB out of that Thevenin voltage, you'll see that it is KB reduces with the frequency. When I say that you are implementing an FEA solution without solving for eddy effects, what does it mean in the circuit level is this branch is not present, right? This is applicable for rotor core or stator core anywhere. So most of the FEA solvers are not suitable to estimate the core losses in the laminated core because that laminations cannot be modeled. It becomes the meshing becomes extensively high. We cannot solve without having some supercomputers. Again, there is a practical problem in doing such kind of like theoretical correctness related problem when you are trying to do that. So what is the general common approach is solve for the B distribution and use the Steinmetz equation locally in each mesh. Whatever is the B there, apply the Steinmetz equation there. Or nowadays there are more improved Steinmetz equation and generalized improved Steinmetz equation that are published. So people are using those equations on the FEA solution, right? So this is something like remove this branch, solve for the back EMF or the current, etc., and then add it and estimate the core losses. You are not accounting for what is the back EMF or what is the torque or what is the magnetic field distribution by keeping the dou A by dou T in the solver, right? Yeah, the problem, let's say we have some supercomputing technology and try to do this lamination based, but it still doesn't address the problem because the core losses are dependent on what kind of manufacturing process you have used, what kind of riveting technique you have used, or have you welded somewhere, or how did you punch it. Based on that, it is said that the core losses change to the extent of you have to multiply whatever you have estimated in FEA solver with 2. I saw this build factor as being given by 2, starting from papers in 1950 to even in 2000. This build factor is said to be about 2. So you got some values in FEA solver about the core losses using the Steinmetz approach, then you have to multiply it with 2. So there is no point in doing this kind of supercomputing based estimation of core losses. Because anyways, it depends on how did you manufacture the motor. Did you press it into the frame, or did you expand the frame and then did some cooling based fitting into that? So all this decides. However, all types of losses get reflect as an increase in Thevenin resistance at the machine terminal. This is something that can save us. Like once you have manufactured the motor, you can do some stationary test or rotationary test to estimate what could be the core loss resistance or additional resistances that are happening in the machine. That is how we can guess this build factor. But it is not possible to say which of at this stage, I mean, with the current methods, where is that particular loss happening? It can be happening because of some shorting between the frame and some electrical connection on the top of the cores, on the top of the back iron, or any additional effects. So this is an interesting topic. Like, how do you where do you put the additional resistance? Where is it happening? Is it the skin effect or the proximity effect, or is it the core loss, or is it the magnet losses? So that is as of now estimated, but not pinpointed that it is happening here or there. So one such example is in some PMSM machines, they use a retaining sleeve to protect the magnets, right? And in applications where these are mass manufactured, the sleeve is used is a normal mild steel. It's a conductive material. So because of the harmonic content, there are additional losses in the sleeve. This also gets reflected as an increased Thevenin resistance when you look from the terminals. But where do you put it? Do you put it here, or is it because of some leakage? These are some interesting things that one can think, and they're still being addressed. Any questions?
Why the sleeve cannot be not?
It's costly. Mild steel paste is the cheapest. So one application where this kind of sleeve is used is engine starting motor. It should cost about less than 2,000 or something. So in very high speed applications where it is sensitive, then they'll go for carbon fiber. So that kind of things cannot go into mass manufactured, I mean, something like two-wheeler applications or even three-wheeler, four-wheeler engine starting application. Yes.
Per meter?
No, the total motor cost.
Sleeve cost?
No, the total motor cost will be around 2,000. So in that they use a very cheap, not cheap, economically suitable material. So that's all. I'm done. If you are interested to read about these FEA methods, these are the 3 books you can refer. There are more, but these are I'm familiar with. And as I said, there is a course that you can do. And what I found is, you want to understand what is happening behind in terms of estimation of inductance or resistance from the FEA step. Open source FEA manuals are more clear compared to commercial package manuals. So one such manual I have suggested here. So I'm done. Any questions? Yes.
Is it possible to have 3D analysis?
No. No, it's a 2D solver. There are other open source. I haven't used them, but there are open source 3D solvers. Problem with open source is it's difficult to use them. I mean, the learning curve is learning takes time to get good familiarity with in terms of making the model and getting the results that you want. These things are made easier in commercial packages. Thank you.